My name is Derek Smith.
My name is Zhipeng.
My name is Ernst, and this is our final lab project using the Caliball to test the zygote interferometer.
This is zygote interferometer, and here is where the transmission server is mounted, and here is where the Caliball plays. Here is how the Caliball is mounted, and we have tip and tilt, and this knob is used for moving the Caliball up and down, and this is for left and right, and here is the fine adjustment for in and out.
At the head of the interferometer, we have two transmission spheres, one with F number 7.2 and another with F number 1.5. Here we have the Caliball and the mount to hold its position.
A transmission sphere is used to transform the collimated output beam of the interferometer mainframe into a spherical wavefront, and this is used as a beam splitter to divide the laser light into separate reference and measurement wavefronts.
So just a quick word on alignment.
At the top, the Caliball's surface coincides with the back focal point of the transmission sphere. This is called the cat's eye. This position is incorrect. At the bottom, the center of the Caliball coincides with the focal point of the transmission sphere. This allows the outer radius of the Caliball to match that of the converging laser light from the interferometer.
We use the tip-tilt adjustments to center few fringes onto the computer, and we use the analyze function of the interferometer to find the intensity graphs to find our PV and RMS values.
We then took 10 separate measurements of the Caliball with each of the two transmission spheres, so 20 in all. We rotated the Caliball after each measurement. This provided a new surface area for each measurement. To ensure against error caused by Caliball surface imperfections, we used MATLAB to average our measurements together. If there were an imperfection in any single section of the Caliball surface, it would be minimized by the other measurements. For the f1.5 transmission sphere, here is the average intensity of the fringes along with the standard deviation. And here is the average phase difference in waves of the zygote's laser light along with its standard deviation. The standard deviation is at approximately 0.01. Due to the low standard deviation, all of our trials look about the same as the average that you see on the left. We see evidence of astigmatism, the lower phase shift in the top and bottom versus the higher phase shift in the left and right. This picture in 3D would look more like a potato chip. Moving on to the f7.2 transmission sphere, this is the average intensity we got, and this is the standard deviation that we got. Notice the plethora of fringes there are. We had a huge difficulty getting fewer fringes than this. When we were getting less fringes, we were actually at the cat's eye position. Here is the intensity plot of the phase for the f7.2 lens and its standard deviation. The standard deviation was approximately 0.07. The astigmatism here is even worse than before. The problem is the lens is too slow of a lens for the size of this Caliball. So if we had a larger Caliball, we could have gotten the cat's eye position further away from the confocal position and had a more accurate measurement. Because we were too far from the confocal position, there was too much astigmatism present to accurately measure the amount of error in the zygote interferometer.